Hi, this is Organized Confusion. We're here presenting our container draining design project. The analysis of fluid draining from a container is important for many applications in the industry. These applications range from safety to flow analysis. Here, we shall compare the theoretical calculations to the experimental data recorded. We shall be calculating and analyzing the time it takes for a gallon of water to leave the container.
For our experiment, there were some assumptions that we had to take into consideration for the calculations. One assumption is inviscid flow. That means that there is no friction in the system. Another assumption is incompressible flow. That means that the density is constant as time changes. Another assumption is that the flow followed a streamline. That means it is laminar with no turbulence. We were unable to assume a steady state because there is no flow into the system. The change in mass with respect to time is only equal to the mass flow out because there is no mass flow in. For a straight edge orifice, the orifice coefficient is equal to 0.61. The traffic cone in our experiment is modeled by a truncated cone. The following are some formulas that we used to determine its basic dimensions. For the volume, it is equal to pi divided by 3 times the large radius squared plus the large radius times the small radius plus the small radius squared times the height of the truncated cone. For the large radius at any height, it can be found by the height of the truncated cone plus 0.187, which is the value from the inner radius of the truncated cone down to the theoretical tip of the cone, times the tangent of theta. For the area of the orifice, it is equal to pi times the orifice radius squared. For the geometry of our cone container, the top diameter is equal to 0.184 meters. The bottom diameter of our truncated cone is equal to 0.054 meters. The orifice diameter is equal to 0.030 meters, and the internal height of our cone is equal to 0.451 meters.
The cone will be sealed with a rubber stopper attached to a string for easy removal. The goal is to add the least amount of vibration to the system. This is done in order to reduce turbulence because turbulence will affect the draining time. As stated before, since the mass flow in is equal to 0, the change in mass with respect to time is equal to the mass flow exiting the container, where mass is equal to density times volume, and mass flow is equal to volumetric flow rate times density, which equals to velocity times the cross-sectional area times density. Substituting these equations into the differential mass flow equation, we get the change in density times velocity with respect to time is equal to negative velocity times the cross-sectional area at the orifice times the density. Continuing with Bernoulli's equation, since pressure 1 is equal to pressure at 2 because they are both in atmospheric pressure, those values cancel out. The density is constant throughout the whole system, therefore all values for density cancel out. The height at the orifice is considered to be 0, so therefore the density times the gravitational constant times h1 cancels out, and the velocity at point 2 approximates to 0 because the velocity at point 1 is much greater than the velocity at point 2. Therefore, the new equation, when solved for the velocity at point 1, becomes the orifice coefficient times the square root of 2 times the gravitational constant times the height. Substituting for the volume of the cone the velocity and the area at the orifice, we get that the change in the volume of the truncated cone is equal to negative coefficient of the orifice times the square root of 2 times the gravitational constant times the height times pi times the radius at the orifice squared. By replacing r with the equation given earlier, integrating the differential, and solving for the value of t, we get the following equation for t. By replacing r with the equation given earlier, integrating the differential, then solving for the value of t, we get the following equation, which estimates the time it should take to drain the container at any given height.
The materials used for the design experiment are a traffic cone, which functions as our container, a cone stand, which holds the container above the sink at level condition, a stopwatch used to measure the time to drain the container, a rubber stopper and string, which are used to plug the container to hold water and is removed to start the flow, and a small graduated container measuring the amount of fluid poured into the container as well as the fluid left over after draining. To set up for the experiment, the cone is placed upside down on the cone stand. The rubber stopper is inserted into the orifice to secure the water as it's poured into the container. The string is inspected to ensure it can be pulled freely to start drainage. To begin the experiment, the cone is filled with the desired volume of water. Once ready, the rubber stopper is pulled from the orifice by way of the string at the same time the stopwatch is started. Once the initial rush of water has exited the orifice and only dripping remains, the stopwatch is halted. The excess water remaining within the container is measured with a graduated container. The data collected during this procedure is recorded and repeated with another desired volume of water.
So the table shown is going to be the theoretical calculations for the volume of water to exit through our orifice, assuming it's a sharp edge orifice, along with our assumptions. For this given demonstration, we use 3.78 liters of water, which is equivalent to 1 gallon. In the theoretical time it should take is 4.67 seconds to drain. So the table shown is from our experimental runs. It shows the average drain time for the given volume of water. We acquired this through empirical methods, and it was determined due to the material properties of the container and the weight of the fluid. As the volume was increased, the orifice coefficient also increased.
The graph shows that as the volume of water drained increases, the difference between the theoretical and experimental drain time diverges.
After draining the tank, there was 0.1 milliliter of water remaining. The initial error was 14.1% using the assumed coefficient of 0.61. After collecting experimental data, we realized that as tested volume increases, the weight from the fluid causes coefficient to increase. Therefore, we calculated a modified orifice coefficient to be 0.75, which reduced our error to 9%. This concludes the container draining project as presented by Organized Confusion.